The ship struck the coral wall as daylight failed. Below the waterline, the jagged edge of the Great Barrier Reef tore into the wooden hull of the frigate Pandora. Water surged into the lower decks. The crew rushed to the pumps. They failed. When the hull finally surrendered and went down on August 30th, 1791, it took 35 men with it. Among the dead were 4 prisoners from the Bounty, lost in the confusion of the sinking, with later accounts differing on exactly who escaped the box, who remained trapped, and who died still in irons. The vessel was a 24-gun Royal Navy frigate, dispatched to the South Pacific in 1790 on a highly specific law enforcement mission. The Admiralty ordered the captain to locate the mutineers of the ship Bounty and return them to England for trial. The crew successfully apprehended 14 of the fugitives in Tahiti. To transport them securely across thousands of miles of ocean, the ship carpenters constructed a dedicated holding facility on the quarterdeck. This structure was a heavily reinforced wooden box measuring exactly 11 feet by 18 feet. The crew referred to the cell as the Pandora box. It featured heavy iron deadbolts and minimal ventilation. The cell was an engineering solution to a human security problem. It was designed to be absolutely inescapable. This design requirement created a deadly geometry when the frigate hit the reef. On August 29, 1791, as the ship worked along the outer edge of the Great Barrier Reef, 18th century navigation still depended on human sight, leadline soundings, charts, compass work, and dead reckoning. Fading evening light and severe tidal currents disrupted the course. The heavy hull drove into a submerged coral outcrop, transferring brutal force into the wooden frames and opening the structure below the waterline. Seawater began breaching the hold. The captain ordered all available hands to the mechanical chain pumps. A sinking wooden warship survives only if its crew can manually lift water out of the bilges faster than the ocean pushes it in. The crew worked the heavy pump cranks and relays for 11 straight hours, driving the internal chains and lifting seawater up and over the side rails. But the pumps could not overtake the flooding. The equation was fundamentally broken and exhaustion mounted as the water rose through the lower decks. By the morning of August 30th, the internal water weight had overwhelmed the reserve buoyancy of the ship, leaving the crew unable to keep ahead of the flooding. After going down, the substantially intact hull settled into the seafloor on its starboard side, where later sediment would bury and preserve much of the lower structure. The sudden geometric shift turned the quarterdeck prison into a deadly trap. 3 prisoners had already been let out of Pandora's box to help at the pumps. At dawn, with the ship beyond saving, orders were given to abandon ship and release the remaining prisoners. The order came too late to save every prisoner. Last-minute efforts opened a route out, but the release remained incomplete under the speed of the sinking. The death toll resolved into 31 crew members and 4 prisoners. The survivors, 89 crew and 10 prisoners, escaped in 4 open boats with very little provision, pulling away from the doomed vessel toward a small sand cay later remembered as Escape Cay. The immediate struggle against the flooded hold was over. Once the hull breached the surface and plunged to the ocean floor, the antagonist shifted from jagged coral and rapid flooding to the severe physical pressures of the outer reef environment. The shattered hull of the frigate rested on the ocean floor between 100 and 110 feet below the surface of the Coral Sea. For 186 years, the exact location of the wreck remained uncertain. The vast expanse of the Great Barrier Reef effectively hid the remains until 1977. A Royal Australian Air Force Neptune aircraft carrying an airborne magnetometer swept over the outer reef. Near the end of the search, the instrument registered a minor disturbance in the magnetic field near one of the predicted areas. The wooden hull itself was invisible to the instrument, but the iron masses inside the wreck were capable of producing the signal. Smoke flares marked the area, and divers later confirmed the site by locating an Admiralty pattern anchor and other fittings. When the first dive teams descended to the coordinates, the work came under strict diving limits. Operating around 100 feet below the surface creates an immediate physiological constraint for human divers. The body itself is not crushed at that depth, but every airspace and every breath is governed by pressure. Breathing compressed gas increases nitrogen loading in the bloodstream and tissues, strictly limiting safe bottom time. The Pandora teams worked under formal diving schedules, using surface-supplied and SCUBA regimes, decompression stops, standby divers, and recompression support. Some working dives at roughly 33 meters required 27 minutes at 9 meters, breathing 100% O2. Other SCUBA work stayed within no decompression limits with a precautionary stop. The severe tidal currents of the outer reef turned those stops into physical endurance events. The divers had to hold position in moving water while their dive clocks, gas loading, and safety procedures controlled every minute of available work time. Reaching the seabed revealed a stark environmental division. The violent cross currents of the reef had initiated a long biological and physical destruction process after the original sinking event. The upper levels of the vessel remained exposed to wave motion, currents, bacteria, and marine wood-boring organisms. Over time, those unprotected structures collapsed and disintegrated. The top half of the frigate was not preserved as architecture, it was broken down by the aggressive environment of the reef. Below the destroyed upper works, sediment cover changed the chemistry and biology of the wreck. Dense marine sand reduced exposure to oxygen, currents, bacteria, and wood-boring organisms, slowing the destructive process that had erased the exposed upper levels. It did not create a perfect freeze frame, but it preserved a substantial section of the 18th century warship with unusual clarity. The internal architecture, structural timbers, and fragile personal artifacts remained protected enough to become a rare archaeological time capsule. The same thick sediment that had protected the historical timbers now acted as an impenetrable vault. The forensic dive teams faced an immense operational contradiction. The heavy sand held pristine artifacts, yet the covering was far too massive to simply brush away by hand. Within those limits, each excavation choice carried a time cost. They could not blindly dig into the compacted seabed without crushing the extremely fragile, organic remains hidden just beneath the surface. Knowing a pristine time capsule lay trapped under the heavy sand, the forensic team faced a new boundary. They had to extract precise spatial data without destroying the delicate context that had preserved the site for 2 centuries. The wreck site was a massive, 3-dimensional field of structural collapse beneath compacted sand. Before any diver could remove timber, fittings, or personal objects, the team had to solve the geometry of the buried ship, because an artifact removed without its position would lose much of its forensic value. The teams faced a severe engineering problem. They were operating in an aggressive environment, fighting violent tidal surges that made conventional measuring techniques completely impossible. A traditional flexible tape measure would stretch, flex, and drag in the heavy ocean currents, severely corrupting any dimensional data. Furthermore, the warship had rolled onto its starboard side as it sank. The surviving architecture was slanted at a sharp angle beneath the sediment, making flat 2-dimensional maps completely inadequate. To solve this spatial crisis, the Queensland Museum took control of the site and initiated a rigorous long-term scientific campaign. They knew the recovery could not be rushed. Their immediate priority was spatial control. The survey teams established a recording grid and datum system directly over the seabed. These rigid reference points gave the divers a stable local framework inside the moving water. By working within measured grid squares, the dive teams could tie each exposed timber, fitting, and artifact back to a controlled archaeological map. Once the recording framework was in place, the archaeological teams introduced a demanding spatial mapping routine. The divers did not immediately bring every historical object to the surface. They tagged finds, photographed many objects in situ, and transferred the underwater data back to the support vessels. Back on the surface, the expedition teams converted those measurements into site plans and artifact maps. In 1984, AutoCAD was used to create the grid and artifact drawings by which objects were located and cataloged. This was an exceptionally early use of computer-aided drafting in underwater archaeology. It did not magically resurrect a perfect virtual wreck, but it preserved spatial relationships after physical recovery began. The divers had brief windows to capture raw measurements underwater, while the surface team could refine those measurements into a disciplined site archive long after each dive had ended. However, knowing exactly where the artifacts were located was only half the forensic equation. The mathematical map could not lift physical history to the surface. The team still had to clear the same heavy marine sand that had preserved the wreck without turning that protection into a destructive obstacle. The archaeological dive teams needed to remove tons of compacted material to reach the lower decks. Traditional mechanical digging tools were far too aggressive for saturated wooden planks, personal artifacts, and buried human remains that had been underwater for 2 centuries. Direct scraping could tear through delicate wood grain and destroy the historical integrity of the structure. Furthermore, the immense weight of the sand was acting as the primary load bearing support for the surviving architecture. The ship had rolled onto its starboard side, and the sediment was packed deeply into the broken angles of the heavy oak frames. Stripping the sand away too quickly or unevenly could trigger a sudden structural collapse of the entire trench, crushing the buried artifacts beneath heavy falling timbers. The excavation required a method that could reduce load without destabilizing the trench. To solve this crisis, the expedition teams deployed a highly controlled, non-mechanical clearance system. They utilized heavy-duty water dredges. A water dredge avoided direct mechanical contact with the buried structure. Instead, the tool relies on strict fluid dynamics. Large surface pumps drove high-pressure water down a rigid pipe from the support vessel to the dive site on the seabed. At the bottom, this high-velocity stream was abruptly redirected upward through a wider extraction tube. The sudden acceleration of the water flow past a restricted neck created a powerful, localized pressure drop. This specific physical phenomenon, known as a Venturi suction effect, acted as an incredibly precise underwater vacuum. The divers did not ram the suction pipes directly into the buried timbers. Instead, they worked with hand fanning and carefully controlled water dredging, lifting loosened calcareous shell debris and fine sediment away from the wreck while keeping hard machinery off the 200-year-old structure. Spoil could be discharged clear of the excavation area, while the divers exposed the hull and artifacts slowly enough to maintain archaeological control. This hydraulic clearance method allowed the team to remove sediment without turning the excavation into a destructive mechanical dig. Layer by layer, the method revealed well-preserved organic material, ship fittings, personal objects, human skeletal remains and fragments, and substantial lower hull structure, including framing, knees, floor timbers, and associated artifacts. The selected deposits transformed a buried anomaly into a controlled archaeological trench, exposing enough interior architecture to read the ship without pretending the entire wreck was perfectly intact. However, the success of the water dredging created an immediate new management problem. Wherever the protective marine sand was opened, ancient wood and fragile objects were exposed again to oxygen, current, and biological attack. The excavation could not simply strip the wreck bare and leave it open. Each selected area had to be recorded, recovered where justified, and then stabilized. At the end of excavation, exposed areas were backfilled with clean sand, covered with protective material, and weighted down, so the site itself remained part of the conservation plan. Site stabilization only closed one problem. The next was vertical extraction through 100 feet of moving ocean. With selected areas exposed, the dive teams faced the immediate challenge of physical extraction. Wood, bone, and ceramic submerged for 2 centuries undergo severe cellular degradation. When an ancient object is pulled from the seabed, it faces violent fluid drag during the ascent. More critically, as the object breaks the surface of the ocean, it immediately loses the buoyant force of the water. Waterlogged wood that feels weightless on the bottom will suddenly collapse under its own terrestrial weight in the open air. To bypass this physical trap, the archaeologists could not simply carry the historical evidence to the surface. The expedition used controlled lifting systems and careful packing procedures. On the ocean floor, divers supported, separated, and secured recovered material according to its shape, weight, and fragility, so objects would not shift, collide, or lose their recorded context during the ascent. The recovery of human skeletal remains required caution and respect because the recovered skeletons could not be identified with certainty. Bone and bone fragments were supported and packed to prevent damage while preserving the forensic information still held in the remains. Hoisting the heavy iron armaments presented a completely different physics problem compared to lifting the delicate organic remains. The massive iron cannons and large anchors had to be slung with heavy-duty industrial rigging. If one of these massive metallic objects slipped from its harness during the ascent, it would plummet straight back down into the open trench, instantly obliterating the fragile hull timbers exposed below. The surface team had to synchronize the crane movements perfectly with the ocean swells to prevent the lifting cables from snapping under the sudden dynamic loads. Once a basket was fully loaded on the seabed, The surface crew engaged the winches and turned the lift into a control problem. Severe crosscurrents pushed against the flat surfaces of the cages, creating a dangerous pendulum effect. The winch operators had to maintain steady tension, while the deck crew brought each load over the rail without letting it swing, twist, or strike the vessel. Surviving the physical lift triggered an immediate conservation crisis. If an artifact that has been submerged for 200 years is allowed to dry in the sun, internal moisture can leave the material too quickly. Wood may shrink and crack, composites may separate, and corrosion products on metals may destabilize. To prevent this catastrophic transition, the surface teams moved newly recovered objects through initial registration, photography, and sketching, then kept them wet while conservators identified the material type. Each object was stabilized and packed according to its own chemistry, rather than forcing wood, iron, bone, ceramic, and composite artifacts through a single treatment path. This slow, highly systematic recovery sequence continued across multiple expedition seasons. By strictly managing physical handling and conservation stability, the dive teams achieved an extraordinary archaeological yield. The expedition ultimately transferred thousands of individual pieces from the wreck to the surface laboratory. Current Queensland Museum figures place the recovered collection at more than 7,500 artifacts, while some project summaries use lower catalog counts of more than 6,000. This massive inventory included heavy iron armament, the ship's galley stove, delicate glass case bottles, and rare Polynesian wooden clubs collected by the crew before the sinking. The success of the vertical extraction rested less on the headline count than on the way each object remained tied to its recorded path from seabed to laboratory. The methodology proved that deep-water archaeological sites could be systematically investigated without sacrificing the integrity of the material. The retrieved cargo answered historical questions while preserving a durable record for future deep-water forensics. The final analysis turned the wreck's uneven survival into forensic evidence. The site showed how exposure, burial, and seabed conditions could divide one wooden warship into two different archaeological outcomes. Wreckage left exposed to the open water column will inevitably face total biological annihilation. Conversely, any structure rapidly buried by the heavy marine sediment will enter a permanent state of suspended animation. This preservation pattern changed how investigators thought about Pandora and about similar reef environments. They no longer had to read the seabed as a simple field of destruction. Sediment movement and burial could become clues to survival as much as signs of collapse. Pandora became an important real-world case study. It demonstrated that the ocean is not just a destructive void, but a complex taphonomic engine that can simultaneously obliterate and protect. For future searches, areas of rapid sediment accumulation became especially important clues, not mathematical guarantees. The lesson was powerful, but it remained archaeological evidence, not a universal formula. Achieving the scientific clarity required an immense and sustained institutional commitment. The sheer logistical scale of the recovery effort demanded 9 distinct field seasons over 2 decades, not one continuous excavation. This was not a singular rapid salvage mission, but a grinding, multi-year campaign of planning, diving, recording, recovery, conservation, and site management. Each field season required mobilizing support vessels, assembling trained dive teams, and working within the hostile weather windows of the outer reef. The Queensland Museum maintained long-term archaeological responsibility for the historical site throughout the sequence. They managed the severe risks, enforced the rigorous safety boundaries, and ensured that the operation never sacrificed data for speed. The legacy of that sustained effort now resides safely on dry land. Today, the vast inventory of recovered materials is housed at the Museum of Tropical Queensland. This facility functions as the final secure vault for the 18th century warship. The collection is not treated as isolated curiosities. Museum curators maintain it as a unified research archive. This extensive archive allows modern researchers to study the strict reality of Royal Navy shipboard life, 18th century naval architecture, and the precise mechanical limits of the era. The collection provides an unbroken physical bridge directly back to the final voyage of the vessel. By preserving the exact physical state of the recovered artifacts, the museum honors the reality of the disaster without dramatizing it. The shattered items and the perfectly preserved equipment sit side by side in the climate-controlled vaults. The historical narrative of the frigate is defined by opposing physical events. The sinking in 1791 was uncontrolled failure, flooding, exhaustion, and structural collapse. The modern recovery answered with measured control, spatial recording, controlled lifting, conservation discipline, and long-term archival care. The expedition did not undo the disaster. It made the wreck legible again and left deep-water forensic archaeology with a durable record of how history survives in the deep ocean.